the actual beam on the structure. So at point A, the support is a roller. At point B, the support is a pin. So this is the real beam. So we need to draw another beam that is almost the same as the real beam, but now in this case it has different supports at both ends. So ideally, a conjugate beam is a beam that is almost the same as the real beam, but having different types of supports depending on which supports were initially on the real beam. So the most important thing to note here is that whenever you are given a real beam, for example, I have several real beams here. You can see them. You have beam A, beam. These beams have different types of supports. So we are only looking at supports. So, for example, look at this beam AB. The support is roller and a pin. So to draw another beam, which is going to be called conjugate, you can see it still maintains the same support. At point A, we still have a roller. At point B, we still have a pin support. So in this case, conjugate beam is almost the same as the real beam. But now look at this other one, whereby beam AB, at point A we have fixed support. Okay. Now we need to draw a conjugate beam. So if you look clearly, at this conjugate beam, this beam, you will find that in the initial beam at point A we had fixed support, but in a conjugate beam it is a free end. Yeah. But at point B, initially we had a free end. In the conjugate beam we have a fixed support. So in this case, you need to know now, if a beam is fixed at one end, to draw a conjugate beam, that end will be free, and while the other end that was initially free, it becomes fixed. Yeah. Now you can also look at this other beam. So you can see this beam ABC at point 8 is a free end. At point B you have a roller. At point C you have a pin support. So we need to draw another beam that is of equivalent, same length, same size as the original beam. Okay, but now the supports are different. So you can look at this conjugate beam now. So you see at point A, initially it was free end, but now for the conjugate beam, it is now fixed. See this red one? Initially at point B, we had a roller. So if we have a roller in the middle, for the conjugate beam, we have a hinge. Yeah, hinge is something that just a hinge. I don't know. It's like a hinge of a door. Okay, which means there is a breakdown between point AB and point BC. Okay, now in the real beam at support C, initially we had a pin support. So if you look at the conjugate beam, it still maintains the pin support. Yeah. So the only thing that is changing here is the support at A and support at B, whereby support at A is substituted with fixed, while support at B, initially it was roller, now it is a hinge. It is very important to know the difference. But the end support at point C, it still maintains the same support. Now, we have another case of a beam whereby point A is fixed, point B is a hinge, and point C is a pin. For the conjugate, we are going to draw the same size, the beam of the same size, okay, same cross-sectional size, but now look at point A. Initially it was fixed, for the conjugate it is free end. Yeah, that's very important. At point B, initially it was hinged. This dot is a hinge. For the conjugate beam, where we have a hinge, now for the conjugate beam it is a roller. Okay. Initially, the real beam at point C it had a pin support. For the conjugate beam, it still maintains the pin support. Yeah. So you can see it is almost equivalent like this one. Yeah. Now we also have another type of a beam here. Initially it is fixed. You have at support B you have a roller, at support C you have a hinge, and support D you have a pin support. So if I ask you to draw a conjugate beam, what we're going to do, because at this end A we have a fixed, you leave it free. Okay, point A is free. Because at point B you have a roller, we are going to introduce a hinge. Because at point C we have a hinge, we are going to introduce a roller. The other end, because it's a pin, we are going to leave it the way it is. So this one is now the conjugate beam of this real beam. Okay. Then we have the last example. We have this beam. So we have a roller at this end, a hinge, and a pin. So it's almost the same. So because this roller at the end, we cannot put a hinge here. Okay. So we're going to maintain the same roller. Okay. But because the hinge is in the middle, we're going to introduce a roller and also a roller, because we have a hinge at point B and C. Then at point D, because it is a pin, we cannot introduce a hinge at the end. It's going to remain with a pin. So ideally, you need to know all this type of, you need to know how to draw the conjugate beam. That's the first step, knowing how to draw the conjugate beam. Because now if you don't know how to draw the conjugate beam, there's no way you're going to proceed with this type of questions. So this one is a must. You must know how to draw a conjugate beam. Now, after knowing how to draw the conjugate beam, now the next step is how to manipulate this conjugate beam to help you now find the deflection of the beam. So last time we met, we were looking at the shear force diagram and bending moment diagram, and I really insisted that you need to know how to draw a bending moment diagram and a bending moment diagram and a shear force diagram for all types of beams. So I want us to look at this real beam and conjugate beam. Now this is just elementary. You know, if the end is fixed, yeah? If the end is fixed, there's no rotation. So the rotation is normally 0. And also the deflection. So this thing is fixed here, so it cannot deflect because it is fixed. Yeah. So in the real beam, you see now in the real beam, we have a fixed support. In the conjugate beam, you see it will be a free end. In the same way, at this end, deflection is 0. V means deflection. V means shear force. At this end, in the conjugate beam, the shear force 0, and the moment is 0. We will see the significance of the shear force and moment. Okay. So the same case to the roller. If the roller is fixed, you know we don't have a rotation. No rotation is there because it's going to rotate like this. So we have this theta here, this point. But we don't have a deflection here because this thing is fixed here, so it cannot move either up or down. In the conjugate beam, the shear force and the moment. We are going to see why we have a shear force and the moment in the conjugate beam. So the same case, the shear force will be 0 at this end. The shear force will not be 0 at this end, but the moment will be 0. Okay. So maybe before we look at all these, let us look at what we mean by conjugate beam. So for a conjugate beam, let me see. So in the conjugate beam, ideally, we are going to look at two things: the shear force and the moment. So we have the original beam and the conjugate beam. So in the real beam, we still have the shear force and the moment. Okay. Also in the conjugate beam, we have a shear force and the moment. So what we are doing, if we have been given a conjugate beam, for example, now let me take an example like this beam here. We have beam AB, which is it can be of any length, beam AB. So now this beam AB, if it is loaded, let me assume it is loaded by a load P at the center. Let me admit more people. Okay. So this beam is loaded at this center with the load P. Obviously, we are going to draw. This load is going to create what we call a bending effect on the real beam. In that case, we are going to draw a bending moment diagram for this beam. So for example, if it is loaded with the load P at the center, assuming it is loaded at point P at the center, so we are going to have a moment diagram AB, bending moment diagram. So the first thing we need to draw the bending moment diagram, okay, for this. So let me say that the bending moment diagram will look like this. It's supposed to be a triangular, a straight triangular, yes. That is the bending moment diagram. Okay. Now this is the bending moment diagram. So we have AB real beam and we have AB the conjugate beam. So maybe let me do like this, so to make it clear. So in the real beam, we can draw the bending moment diagram, okay, in the real beam. This is the bending moment diagram in the real beam. Then now this bending moment diagram, okay, we transfer this, or before we transfer, we say M divided by EI, okay. We divide this moment by EI, okay. So the moment that we have gotten from the real beam, we divide it by EI. Then the same thing, we transfer it into the conjugate beam. Okay. Now this moment now becomes the loading on the conjugate beam. Now becomes the load. Okay. So remember initially the bending moment diagram was triangular. This load is M over EI. Now it becomes the load on the conjugate beam. So you see now, first step, draw the bending moment diagram, okay? This case, because the load is a point load at the center, the bending moment diagram is going to be triangular. Then take that bending moment diagram or values, divide them by EI, then transpose them on the conjugate beam, okay? They have done. So now this one, I've divided by EI to become the load on the conjugate beam. So once you have done that, you now look, now we have a loading AB, it's a triangular load, okay? So let me say this point C and this B. So this is a triangular load on the conjugate beam. So this triangular load is going to impose two things. We are going to have the shear force V, and we're also going to have a moment on the conjugate beam. So wherever you find the shear force, for example, if I ask you to find the shear force at point A, okay? The shear force at point A, the value of shear force at point A will be the rotation theta. I hope I'm clear with that. So the value of shear force at any point between point A on the conjugate beam will be the rotation, which is theta. The value of moment at any point on the conjugate beam, this M, will be now the deflection, okay? Is there anybody who has a question up to that place? Because if you don't understand that, then you cannot proceed. So is there anybody who has a question up to there? Before we proceed. Anybody who has a question? Okay. Simbine, you have a question?
Yes, thank you. My question is,
yes.
Is there an explanation why we are using the theta to find the value of shear and the moment, and for the moment we are using deflection?
Is there an explanation why we are using that? So this one has been, what can I say? This one has been, it has been proved, yeah? It has been proved. There are other equations that have been used to prove that if you find the shear force at any point on the conjugate beam, that will be the rotation at that place. There are also equations that have been used to prove that if you find any moment at any place on the conjugate beam, that will be the deflection. So maybe I didn't go into that detail very much, but it has been proved by someone else. So we are just using those equations as a means of finding whatever we want in terms of rotations and deflections. Yeah. Have I answered your questions? So we have there are questions that have been derived and have been successfully shown that the shear force is equivalent to rotations and the moments is equivalent to the deflections. So we are just using basic them. Okay. Unless we have another question, so let's continue. So now we know how to find now we know how to draw the conjugate beam, and now we know how to find the way we find the shear force and the moment in the conjugate beam is the same way we were finding them in the real beams, those ones that we are looking at last time. So the only difference here is that this is a triangular load. So we need to know how to find the shear force when the beam is loaded with a triangular load. Okay, that's the only problem here, the only difference here. And also sometimes when the beam is loaded with the UDL, okay, UDL will create a parabolic. It will be like this, parabolic curve. So you need to know how to find the shear force and also the moment when the load is parabolic, because you know the UDL is going to create a moment that is parabolic. So we had this thing here. I don't know if you can interpret this curve. So this curve we have h, height, and b, which is length. So to find the area, because sometimes you need to find the area. Let me admit this person. So you can look here. So if area 1, n is the equation degree. So for example, if n is equals to 1, it is now a triangular, okay? If n is equals to 1, this one is a triangular. So the area is just a half times base times height, okay? The center of gravity, the middle, you see where it applies. The center of gravity, you know, if it is a triangular, if you are coming from this side, going this side, the center of gravity from this side is normally a third times base. If you are coming from this side, from this lower side, from this lesser side, the center of gravity, the distance from here to where the center of gravity is, it is 2/3b. Okay. So if it is a parabolic, if it is a parabolic, the area you're just going to replace, parabolic means it is something like this. If you need to find the area, so the formula of getting the area is here, okay? If it's a parabolic, in that case, it is a distributed load. In this case, distributed load. So n is equals to 2, so just replace n2, okay? To find the area of this place, just replace n by 2. And so n will be 2 here, so b will remain this b, h will remain this h, and this one 1. So that then we can help you to find the area. X1 is the center of gravity or the middle of that area up to this side. So just replace x1, it will be b over n. So in this case, n is 2 plus 2. So x1 from this end, the center of gravity is going to be b, this b divided by 2 plus 2. So it is b over 4. If you are coming from this side, this is x2. If you are coming from this side, this x2 it will be, so 2 plus 3 over 2 times x1. So x1 is the distance from here to here, the one that you have found initially. Okay. We'll see how we are going to use these figures. So let me look at the example here. Just an example here, like this one now. Let me look at this example. I want to look at this example, this one here. This one can make it, yes, this example here. So the question is, find the rotation, the support, and deflection at point C in simply supported beam below using the conjugate beam method. So you want to find the rotation at the supports and deflection at point C using conjugate beam method. So this thing is just simple. The first thing you do, from this loading, find the reaction at A and B. Okay, this one you can find just the way we were doing last time, that RA plus RB is equals 24. Okay, then you take the moments at A. Okay, so if you take the moment at A, it will be by times 10 minus 24 times 5. Okay, is equals to 0. So the moment at A should be equal to 0. That one is going to help you to find the reaction at A and the reaction at B. So we are going to use the same method we are using last time to find the reaction at A and also the reaction at point B. Now, once we find those reactions, this case BY, point B is 12. Let me write here 12. And the reaction at point A, also 12. 12. So it is 12, 12. Now from this, we are supposed to draw the bending moment diagram. Okay, they were doing last time. So just draw the bending moment diagram using these values. That's why I was emphasizing that you need to know how to draw the bending moment diagram. So this is a simple case. The moment at A is 0 because it is pinned also. If you look at this side, there's nothing here, so the moment is 0. Also look at this side, there's nothing, so the moment at B is still 0. Then at point C, the moment will be just RAY times distance from A to C. So in this case, it is 12 times 5, so it is 60. That's why it is 60 here. Yeah. So once you get that 60, the next step is now to draw the conjugate beam. Or before you draw the conjugate beam, you can divide that 60 by EI. I told you need to divide. I don't know if it is still here. You need to divide, yes, M over EI. So the moment at all the places, please divide it by M by EI. After dividing M over EI, take that one as the loading and put it on the conjugate beam. See, now it is here. Yes. So we have divided everything by EI, because now we only found the moment here, the maximum moment, which is 60. We divided by EI. Now we need to draw the conjugate beam. So if you look clearly, the original beam was at point A we have a pin support, at point B header roller. Okay, so to draw the conjugate beam, this one will not change. Support at A will not change, support at B will not change, because you can look here. Look at this one here. Yes, so this one, the conjugate did not change. Just roller still maintains roller, pin still maintains pin. So the same beam, but now the support still remains the same. Now you put that moment divided by EI as your loading. So you can see this one is now a loading. Okay, now this one is now a triangular load. So given this load, are you able to find the reaction at A and the reaction at B given this loading? That's now the only challenge there. Okay, how do you find the reaction at A and the reaction at B? You still maintain the same way you are doing it. VA plus VB is equals to total of this load. So how do you find the total of this load? Because it is a triangular load, you're going to find the area of this just half area times height. Okay, also this section, so we have two sections, A and B, and this one B. So this one, it is half times A, half times from this to the center, it was 5. So the area is half times 5 times height. Okay, which is 60. So from here to here is 5, from here to here is 60. That is the total loading. Again, also, the loading on this side is half times base times height. So maybe because it is asymmetrical, we can just say half times base times height times 2. That will be the total loading. So VA plus VB is equals to this whole loading. Okay. Then now we take the moments at point A. Yeah. So if you take the moment at point A, so you find that VB times VB times from here to here it is 10 minus, so this loading, you see this, the first triangular loading, so this triangular loading, it starts from this, let me say this one is C. Okay, so if you take the moment at A, which is equals to 0, is equals to VB times 12, times 10, the distance from A to B is 10, minus, this loading is a half times AC times C times this height, okay, that's the total area, times the distance from VA to the center of this triangular loading. So what is the center of this triangular loading from this smaller side? You can, this one here, yes. You can now come and refer here. Assuming this is a triangular loading, you can now come and refer it here. I have this one you can use as our reference point. Yes, so this one is there. So n is equals to 1. So from this smaller side, what is x? This one is x2. From this smaller side, I said it is just 2 over 3 times base. Okay. So now this center here, this center, let me say the center of this triangular load, it is 2 over 3 times base, which is AC, which is 5. So it is a half times AC times height, which is 60, loading times the distance from this A to the center of gravity, which is 2 over 3 times AC. We'll have finished with this part. Then now we have this one also. Again, to find the moment, moment is load times distance from A. So distance from A to the center of gravity of this triangular will be AC plus 1 over 3 CB. That's the distance from this, from point A to the center of gravity of this triangular load. Okay. Then the loading, total loading is half times CB times height. Height is 60 over EI. Okay. I don't know if you are together, or we can use this. We can follow this. We can follow this. This one here. Let us follow this. So sum of the vertical force is equals to 0. So you see the vertical forces are basically the RA and RB. So is equal to 0. It means RA plus RB minus the whole of this loading should be equal to 0. So if you look here, 150 over EI. So 150 over EI is this total load. Can someone tell me how they found 150 over EI? How the total load of this thing came to 150 over EI? Can someone tell us? So maybe it is just a half times base times height, basic meter. So you can just Elvis. Elvis, do you have something to say?
Yeah. Actually, I do.
Yes.
I was wondering how people understand this stuff, man.
You're wondering how
other people understand these things, man.
They look tough, eh?
It looks like another language. I can't. It just looks like numbers and triangles and rectangles.
Okay, how many people are not understanding anything? So that's why I'm asking now. Can you just say where you have not understood so that we go together? Maybe I can also know where to clarify.
Personally,
yes.
You lost me from where you said that we should know how to find moments and it was moment and
shear force.
And shear force. That's where you lost me.
Moment and shear force. Okay. Somebody else? You need to speak up, Parakaraka, so that I know those who have raised their hands. Can you just say where I lost you?
Finding VA and VB
Finding VA
and VB
in real beam or conjugate beam?
conjugates.
Conjugate, eh?
Yes.
Another person.
What is EI?
What is EI? Another person. So EI, let me answer you. EI is the Young modulus E times E is the elastic modulus, I is the moment of inertia. I'm not sure if you have ever come across those two terms. Have you ever come across them? Elastic modulus E and I is the moment of inertia.
No.
You have never come across them. You have not done any strength of materials. Okay, you are normally given E, the elastic modulus, are normally given from the shear stress. I don't know if I drew for you the stress versus strain diagram, but there is where we find E. The ratio of stress divided by strain is just stress divided by strain. I, moment of inertia, it depends on the section. In most cases, a rectangular section is normally B times D cubed divided by 12. All in all, sometimes EI is normally constant. You can sometimes you can be asked to leave your answer in terms of EI, or you can be given the value of EI. In that case, you're just going to divide 60 by that value. So in this case, it will not matter so much. You are either going to be given or it remains EI as constant. Now, the person who said it, you're just seeing triangles and what. These triangles are not just triangles. This triangle is the bending moment diagram from the original beam. If you know how to draw the bending moment diagram here, now you see here, let me use this one here. This one. If you have a loading, if you have a beam AB, na kuna loading hapa katikati, na mtu anakuambia can you draw the bending moment diagram of this beam? Nani hawezi chora? Is there anybody who cannot draw the bending moment diagram? Huh? Kuna mtu mwenye hawezi chora hiyo? So if you know how to draw the bending moment diagram of beam AB, given the loading of 24 kilonewton at the center C, it will come out to be like this triangle. Okay, this triangle is the bending moment diagram of beam AB given the loading at point C. So it's not just triangles. Now this triangle here, which is the bending moment diagram with its own values, okay, the maximum value is 60 at the center. Just divide that 60 by EI. Yeah? Just divide it by EI. After dividing it by EI, bring that triangle and use it as loading on the conjugate beam. Yeah. So that triangle now becomes the loading on the conjugate beam. Yeah. You see now here. We have now loaded our beam, our conjugate beam, with this triangular loading, which is equivalent to the bending moment diagram of the original beam. Yeah. So I hope that one is now clear. So what we did not do last time is to find VA and VB when the loading is triangular. Maybe I forgot to, maybe I could have done that. When the loading is not a point load or UDL, when the loading is triangular, how do we find VA and VB? The reaction at A and the reaction at B when the loading is triangular. Like in this case, now we have a triangular load, which is starting from 0 up to the maximum point, which is 60 divided by EI. Then we go back to 0. But it is still simple. If you have a triangular load, an increasing load, total load of this thing itakuwa ngapi? Total load itakuwa ngapi? If it is a UDL, for example, if it is a UDL is normal flat, okay? I'll have somebody ask you to find the total load. How much will it be? Let me say this one is 60 kilonewton per meter. Kilonewton per meter. What will be the total load? Let us start from there. Total load from A to B, if it is a UDL of 60 kilonewton per meter, what will be the total load? Can somebody tell me, if beam AB is loaded by UDL of 60 kilonewton per meter, what will be the total load? The AB is 10 meters. What will be the total load? Yes? Are we together? Or you are lost? So you know now the total load will just be 60 times length, because it is 60 kilonewton per meter. And you know the total length from A to B is 10 meters. So the total load is just 10, which is 600, okay? So the total loading is 600 kilonewton. But now this one is now a triangular load. The load is increasing from 0 to 60, then from 60 to 0. What will be the total load? Total load will just be simple. It's a half times base times height, okay? Plus again half times this base times height, because this triangle and also have this triangle there, yeah. So now you see now this one being a symmetrical triangle, you can just say the total load is a half times 5 times 60 times 2, yeah, which is 150, because a half times 5 is 2.5 times 60 is what? It is 30. Okay, let me say a half times base times height. You can say a half times base, which is 5 times height. That is that's how much? Half times 5 divided by 2, 2.5 times 60, it is 150. So it will be 150 over EI, because we have this EI. This EI. So the total load for this side is 150 over EI. Total load for this side is also 150 over EI. So from there we can get VA and VB. VA is just the normal reaction at A. VB is the other normal reaction at B. So reaction at A plus the reaction at B should be equal to the total loading, okay? Should be equal to the total loading of this triangular load, yeah? So up to there, is anybody who has a question up to there? So once we find the reaction at A and the reaction at B, in this case, reaction at A is 150 over EI. Also, the reaction at B is still the 150 over EI, yeah? This one. Because the name is symmetrical, so we expect VA and VB to be the same. Just like in the original beam, RA and RB should be the same. 12 plus 12 is equal to 24. Same case here. So RA, VA plus VB, 150 over EI plus 150 over EI should be equal to this, the total of this triangular load, which is just 150 over EI times 2. Okay. So I hope I've answered the person who asked how do you find VA and VB? So once we find VA and VB, which is basically the reactions, we now need to find the shear force at any place on the beam. Okay. Now, VA at point A, what is the shear force at point A? We found out the shear force at point A, because if you draw the shear force diagram, at point A will go up with 150, okay? This 150, Then we are going to, because it is a triangular load, the loading is increasing. So we expect the shear force also to be reducing up to this place. Okay. So here it is 150 over EI, and also this other side should also be 150 over EI, because we have found out that the nini is symmetrical. Okay. Yes. So we said originally that the shear force in the conjugate beam is equivalent to the rotation, isn't it? So this 150 over EI is just now the rotation at point A. Also this 150 over EI at point B is the rotation at point B. So you have already answered the question. Yeah? The rotational support. The rotational support A is equivalent to the shear force at point A in the conjugate beam, which is 150 over EI. The rotation at point B is the shear force in the conjugate beam at point B, which is 150 over EI. So you can see how simple it is. Once you find the shear force in the conjugate beam, those are the rotations. Yeah. Okay. What about the moment? Now the moment is equivalent to the deflection. We have been asked to find the moment at we have been asked to find the deflection at point C. This point C here. So we are going to find the moment in the conjugate beam at point C. Okay. So how do we find the moment at point C in the conjugate beam? So now you need to have understood, first of all, you need to go back and see how to find out the moments in a beam. If the beam is loaded with a triangular load. Now this one is simple. The loading is triangular, okay? At point C, the loading is 60. Here, 60, okay? VA is 150. 150 over EI. Over EI, yeah? VC, shear force at C is still 150 over EI. So you can see how simple it is how to find the moment at point C. You can either look on your left or look on your right. Okay? When you look on your left, moment will be what? Moment will be VA times distance from A to C minus this triangular load, minus the total of this triangular load times the distance from the center of gravity of this triangular load to point C. Yeah? Just like that, eh? Tumeelewana mpaka hapo? Anybody who has a question up to there? Okay, so this case, the deflection at point C, let me see. The deflection at point C. So look here, you can look at this there. So the deflection at point C is 150 times 5. This 5 here is the distance from A to C, which is 5. Minus, so this one here is the value of the total load of this triangular loading. Okay? So this triangular loading, I told you it is just a half times base times height. Okay? So in this case, it is a half times base, which is from A to C, which is 5. This one is 5. Okay? Times height. Height is 60 over EI. So this one is a half times 5 times 60 over EI. Then times the center of gravity of this triangular load from point C. The distance now is the distance of this loading is the distance of its center of gravity, the point where the center of gravity is to point C. So the center of gravity here, it is if you are coming from this larger side, it's normal a third. So that's why you are seeing this a third times 5. 5 is the distance from A to C. Okay. minus MC. So this MC is what we need, so you can just put it is equals to MC this side. So that's what we are trying to look for. Yeah. So MC is just this loading 150 over EI times 5 minus this total of this triangular load times distance from its center to point C. And in that case, if you calculate it, you find 500 over EI. So you find that the moment at point C is 500 over EI, okay? And that is the deflection. That is now the deflection. So just as simple as that. Once you know how to find the shear force in the conjugate beam and the moment in the conjugate beam, you have already known how to find the rotations. You'll have already known how to find the deflections, okay? That is it. Anybody who has a question up to that place? So you have this. I sent you these notes. So please try to go through this example. I think it is just something very easy to understand. You can just follow this example. There's nothing hard here. It is just an equivalent of what we were doing last time, except that now we are introducing another beam, which is called the conjugate beam. And the conjugate beam, the most important thing is to know the supports, how the supports are being changed. If you have this support, if you want to draw the conjugate beam, how the supports of the conjugate beam change. Okay, that's the most important thing to know. Once you know how to draw the conjugate beam, you take the bending moment diagram of the real beam, you put it on the conjugate beam, then you now find the reaction, which will be the shear and also the moment. Okay, the shear will be the rotation, the moment will be the deflection. That's all. Yeah. So you have another example here, which is almost the same like the other one. This one is almost the same. It's because now the only difference is this load is now not acting at the center. It is acting at 9 meters from point A and 3 meters from point B. You see that RA and RB, we are going to use the normal way of finding the reaction, the way we were doing last time. That's the normal way. At A plus RB is equals to 8. Then take the moment at point A. That's going to help you to find the RB. Okay, once you get RB, subtract from 8 to find RA. It is here. If you do that, RA is here. AY is 0, no, AY is 2, and BY, RB is 6, and RA is 2, which is RA plus RB is equals to 8. Once you find that, please, can you draw the bending moment diagram? Forget even about the shear force. This one is not even necessary, okay? This one, don't draw this one. One is not necessary. Please don't draw it. What you need to draw is the bending moment diagram using this value of RA and RB. Use them to draw the bending moment diagram. We're going to come up to something like this triangular. Divide this triangular by EI. Okay. See now this 18 has been divided by EI. Then use this one to load it on the conjugate beam. Okay. Once you load it on the conjugate beam, now find the reaction again. We are going to use the same way we have found the reaction in the original beam. The same method, we're going to use it in the conjugate beam. VA plus VB is equal to the total of this loading. Okay. Total of this loading, you can divide it. Yeah. Because we have two different triangles of different height. Yes, Elvis?
In this question over here,
Yes.
we can say that we have a loading of 8 kilonewtons here.
Yes.
But then after the triangle has been drawn, we are using 18.
18, eh?
Yeah. So how does that come about?
Can somebody answer that question? I believe there is one person who have heard what I've said. Can somebody try? Where 18 is coming from?
Can I try?
Yes.
I think it's a half times the total length, which is 9 plus 3, then times 8.
A half times
A half times 12 times 8.
anybody else to try. It is not like that. It is not like that. It is not like that. Anybody who can tell us where the 18 is coming from?
18 is the moment at C.
Yes, 18 is the moment at point C. Yeah. 18 is the moment at point C. Please remember that. 18 is the moment at point C. Because we said the original beam, we are supposed to draw what we call the bending moment diagram. And if you draw the bending moment diagram, you'll come up with something like this, whereby at point C, you are going to have 18. Yes. Then now we can divide that moment with EI. Then now you can use that one as the loading on the conjugate beam. That's what they have done here. We have divided this 18 by EI and use it to load it on the conjugate beam. You see now, once you have this, now it becomes easier. Find the reactions. VA plus VB is equals to, because now here we have two triangles. You can separate them. Half times AC times, let times height. Half times AC, height will be 18 over EI. AC is 9, so half times 9 times 18 over EI plus half times 3 times 18 over EI. That will be the total load. So you expect that VA plus VB is equal to this total load. The same way we were doing here, RA plus RB is equals to 8. Okay? In this case, VA plus VB is equals to total of this load. As simple as that. Then after finding, that will be the first equation. Then the second equation, you can stand at either point A or point B. Then you say the moment at A is equals to 0, which is equals to VB times 9 plus 3, which is 12, then minus, now you see here we have two triangles. So we'll tackle triangle by triangle. You can start with the first triangle. Moment of this first triangle. Can somebody tell me the value of the moment of this first triangle from point A? Loading times distance. What will be the load for the first triangle? Anybody who can try? The loading of the first triangle will be total load, because moment is load times distance. So this is a triangular load. A triangular load is just base times height. Total load is just a half times base times height. So for the first triangle, it will be a half times 9 times height, which is 18 over EI. That is the load. Then distance of this first triangular load, the distance you'll find the distance of the center of gravity of this triangular load. Where is it? And Mesema, if you are coming from this smaller side, the distance will be a half time, 1 over 3 times base. You can refer it here. You have this. This one. So you can convert this one, instead of being a parabola, it becomes a triangle. So it's a half times base times height. Okay? Yes. That will be the moment of the first triangle. Then you also have you have the second triangle, this one. We're taking the moment at point A. So you divide first triangle, second triangle. So this second triangle, the loading will still be half times 3 times height, which is 18, then times the distance from point A to the center of gravity of this triangle. Okay? Where is the center of gravity? It is 9 from here to here, from A to point C here, 9 plus, because now we are coming from this bigger side, 9 plus 1 over 3. No, this side is 2 over 3 base. From this side it will be 1 over 3 times 3. Okay, that will that. So the distance will be 9 plus 1 over 3 times 3, which is 1. So from here to the center of this triangle is 10. So the moment is just half times this 3 times 18 over AI times 10 plus half times 9 times 18 over AI times 2 over 3 times 9. Okay, is equals to 0. So from there now you can find the VB and VA. Once you find VB and VA, that's already the rotations. You don't need to calculate more. If it is the deflection at point C, so you can stand at point C and find the moment at point C. How do you find the moment at point C in this triangular load? It will be VA times 9 minus this, the loading of this triangular times its distance from the center of gravity to point C. As simple as that. Or you can use this other side. I told you can look at from any side, either from the left or from the right. You can, the moment at C will still be VB times 3. In fact, this side will be easier. So the moment at point C will be VB times 3 minus half times 3 times 18 over EI times the distance from the center of gravity of this triangle to point C. The center of gravity of this triangle from point C, in this case, it will be 1 over 3 times 3. And that will be the deflection. Okay. So just like that. So conjugate beam method is not a hard thing once you know how to find once you know how to draw the bending moment diagram. It will not be hard, because in this case we are just dealing with the very simple beams. So you can follow the same thing like this one. This one is a cantilever with the 4. So you expect RA to be 4. Don't even calculate the reaction at 8.4. Then you can draw the bending moment diagram on the conjugate beam. You need to first of all you need to draw the bending moment diagram for this thing. So if you draw the bending moment diagram, it's going to be like this. There's no need of drawing the shear force diagram. Don't draw it. Just draw the bending moment diagram. It will come up something like this. Okay. Then that thing you can divide it by EI, and you load it on your conjugate beam. Now you can now see here the original beam SC at point A it is fixed. Okay. At point C it's free. When you want to draw the conjugate beam, at point A it's free. At point B, it is now fixed. Please, I normally see students just using the same beam. Yeah, I don't know why. When you have said we are loading on the conjugate beam, which is a different beam from the real beam. Yeah, that's the first thing you need to know. A conjugate beam is a beam of the same cross-section, same length as the original beam, but the supports change depending on the supports of the original beam. Yes. So if you do that, you can now find the shear force. See, the shear force in this case will remain to be 12 over EI, and this one is the rotation at point B. What about the bending moment at point B? It will be the shear force. So to get the bending moment at point B here, it will be 12 over EI times this distance from here to point B, then minus total load of this triangular load, it will be half times 12 over EI times 3 times the distance from the center of gravity of this triangular load to point B, which in this case, because we are coming from this smaller side, 2 over 3 times 3. Okay. Yes. So this example, this example, there's also another example here. It's now like this example here. What is changing here is what now? If you are given this, you should be able to draw the bending moment diagram, the original beam. Yeah? First of all, find the reaction, point A and B, and then draw the bending moment diagram. So if you draw the bending moment diagram is this one, you can practice it. Drawing the bending moment diagram given this type of beam. Then from there, divide it by EI, then draw the conjugate beam. So you can see this conjugate beam. At point A, it is a pin, it remains to be a pin. At point B, we have a roller here. So because we have a roller here, the thing is going to change into a hinge. So a hinge, so just know that a hinge, whenever you introduce a hinge in the middle of the beam AB and beam BC now become separate beams, okay? Because now you have, it's like you have cut into two, yeah? So there's no relationship between beam AB and the beam BC, yeah? That's what we mean by a hinge. Then the other end, because it is free end, it now becomes a fixed end, okay? Then now you can load it using the bending moment diagram, use it as load on the conjugate beam, and from there you can find the shear force at all the points, point A, point B, point C, and also find the moments at any point, and the moments will be the deflections, shear force will be the rotations. So do you have any question up to there? Because we want to stop from there. Next time you're going to look at the other method, which is the double integration. And I believe when we meet, we need to do the first cut. First time is not on our side. Yes, Jane.
Excuse me, I have a suggestion. Can we be doing these classes on physical instead of online?
We will have to learn them. It will be both online and physical.
Because
So,
I was
like-
thinking,
Uh-huh.
when we have some calculations,
Uh-huh.
we do it in the physical. It's much easier to understand than online. If this has something to do with some theory,
Uh-huh.
can do it online, no problem.
Okay. Yeah, so maybe if I come, if we meet maybe next week, we will. Yes, Isa?
I have a question
Yes,
on the conjugal beam,
yes.
those numbers of load,
Those numbers of load, yes.
Yes. Do you just put them, those arrows, the exact numbers, or you just draw them the way they are on the conjugal
Or
beam?
these arrows, These arrows, there is no definite number. You can even draw 2 arrows or even 10 arrows. It is just an indication of the direction which loading is going.
Okay.
Yes. Another question. So if we meet, we just do one example. Okay, we are not going to do introduction and whatever. Yeah, we still have another class this week, isn't it? I believe we still have another class, Class rep.
No, we don't.
Where's the class rep?
Yes, there is another.
There's another class, So what I'm thinking, we are still going to have another online class on the double integration. Then when we meet, I'll do an example on conjugate and one example on double integration. Then we move to the other thing, because this week I'm not around, but we need to move because we are late. Yeah. So just do one example on conjugate, then another example on double integration. Then we move to virtual work method. I think that will work, because if I say we wait until physical, we might not catch up. Time is not on our side. And now that the next week we are going to have the first cut. So next week, the first meeting will be physical. So I'll do that 2 examples and move to virtual. Then the second meeting to be now cut 1 together. So you have these notes. Please also try to go through them and also try to look at the notes that we did last time. I believe They're almost the same. There's nothing different. Everything is just the same. So you can be able, even this conjugate B method, you can be able to follow it very easily. Yes. So unless we have another question, maybe we can just now meet next time and try to be logging in early if it is online class. So we can end the class. We'll meet next time. Class rep, do you have the attendance list? You have 2 class reps here, isn't it? Because I need those attendance list. So please, when we meet next time physical, please come with them because I need them. I need those attendance list. So please come with them, let them sign. Okay, we'll see. We'll meet the other online, then we'll meet physical. Okay, goodbye.